of new material for fundamentals of digital signal processing, and for this we'll be talking about the second part of multi-rate digital signal processing. So this is part 2, and particular for this week we'll talk about multi-stage, multi-rate, and Z transforms of multi-rate systems. So part of the Z transforms stuff is a little bit challenging. That's a little bit small, so I'll try and make my writing a little bit bigger than that. Okay, so the idea of the multi-rate system we covered last week about changing the sampling rate, essentially, that we're using in our system. You might remember from last week that you were either upsampling or downsampling to change the sample rate. Although we didn't talk about it last week, you can also change by a sort of rational number. By, if you want to change to 3/4 of the sample rate, you could upsample by 3 and downsample by 4, and you'd get to 3/4 of the sample rate. So you can also do that. But one of the key things that we had to do as part of our system was to introduce low-pass filters. Required. So if we're downsampling, we have the low-pass filter first and then do the downsampling. If we're upsampling, we have to do zero stuffing or interpolation, and then use an interpolation filter, which is a low-pass filter. So we've got two different places where we might use the low-pass filter. Now, the key point of the multi-stage version is that it may be more efficient to, let's say that we want to decimate in several stages. So far what we talked about was using a single filter to create a low-pass filter for decimation, which we then reduce the sampling rate all in one go. But if we wanted to reduce the sampling rate by a large fraction, it might be an advantage for us to get sort of halfway there and then do the next stage as the remaining bit of the downsampling. So this is the single stage version. We start off with our system at our sampling rate fs. We do a low-pass filter, which then goes through a decimation process, and we showed this as a down arrow. So here we've got a low-pass filter. Here we've got our decimation or downsampling stage. And so here we were at our sample frequency fs. Here we're at fs divided by d. So this is the single stage version that we talked about it before. We need to design this low-pass filter and then decimate. But a multi-stage version we might go through different stages. So we would have a low-pass filter followed by a decimation in one stage, followed by another low-pass filter, and another decimation. So we might have a low-pass filter 1 and downsample by D1, and then a low-pass filter 2 and downsample by D2. So here we'd end up with our initial sampling frequency here, same sampling frequency, decimate by that, so that's Fs over D1. And then the next low-pass filter, so we're still Fs over D1, and then finally, after also downsampled by another D2, Fs over D1, D2. So you might think, what's the point of this? And the point of this is that it may be easier to design these low-pass filters here and here if we're going through more than one stage. It's not obvious why this might be at the moment, but in some cases it can be easier or more efficient for LPF1 and LPF2 to design those rather than having one filter all in one go. So let's just try this and see it working out. I think the best way of this is to show it by an example, and we can also illustrate what shortcut we can do through this. So for example, the low-pass filter here, just looking ahead a little bit, because this low-pass filter is going to remove some things, it means that this low-pass filter can have an easier transition band because there's some stuff we're not going to care about because it will be thrown away at a later stage. So that's going to make this filter easier to design, and also this filter is going to be at lower sampling rate already, so that will be easier to design as well. So this is where we're heading towards. So first of all, let's look at the type of filter that we're going to design and how we're going to estimate the sample rates for it. So for FIR filter order, so this is the size of the filter, we can design different filters with different windows. We did this a few weeks ago. But just in general, there's a formula that, if we need, will be given for how we can design these. Let's just design a filter with sort of specification that we might want. So here's a filter specification. We've got F2 and delta 2 in terms of, this is our magnitude response here. We've got magnitude response of 1 in the middle with a 1 minus delta 1 and 1 plus delta 1. So we've got delta 1 is our ripple in the pass band ripple. Delta 2 is our stop band ripple here. We've got our pass band edge F2, so this is our pass band, sorry, F1 is our pass band, F2 is our stop band. And then this gap here is our transition band. And the transition band, just push that up, transition band with delta F is F2 minus F1. So that's the width of the transition band that we've got here. So this is the type of filter that we've designed. Sometimes we use F, sometimes we use omega, but this is the same sort of filter design specification that we've had in Lab 4 and that we'll have similar in Lab 5 for our IIR filter design later on. But a guide for the complexity of the filter that we need is that the number of taps or the order of the filter, this is a formula that you'll be given if you need it, 2/3 of log to the base 10 of 1 over 10 times delta 1 times delta 2 times Fs over delta F. Okay, so let's have a look at this formula for a moment. Ignoring the constant, what this says is that the higher the sample rate Fs, the higher the number n that we're going to need in terms of the order of the filter. Also, the shorter the transition band, delta F, that also, if delta F is small, then our order has got to be larger. That makes sense. So it says if we've got a really tight transition band, we've got to cut off really quickly, we're going to need a higher order filter. Similarly, if the pass band ripple delta 1 or the stop band ripple delta 2 are smaller, that also increases n. Okay, this term's inside a logarithm, but it's still an increase. So the tighter we want those to be, then the larger n has got to be. So if we want to make our filter as efficiently as possible, we need to reduce the sample rate, we need to increase the transition bandwidth, or we need to make sure that these delta 1 and delta 2 pass band and stop band ripples are as large as possible. So if we do those, that will make our filter much easier to design. So where we're going to be heading with the multi-stage, multi-rate is we're going to reduce the sample rate and reduce the transition bandwidth in what we're going to try and do. So let's have a look at, as an example, where we're going to do this in a single stage first. Yes, question? So we want to increase the transition band. Yes, sorry if I said reduce, my mistake. So we want to increase the transition band. The wider we make the transition band, the easier it is to design the filter. Yes, so increase the transition band, reduce the sampling frequency, and increase these ripples. So make the ripples as large as possible. That also makes it easier to design the filter. So this is an approximation, but it's one that we'll be using for the work going forward. So let's have a look at an example of what we might want to do. So if we've got a sampling frequency, Fs is 96 kilohertz. We've got a pass band edge F1 of 2 kilohertz, and suppose we wanted a stop band edge F2 of 2.5 kilohertz. So we're going to do some downsampling, so we're only going to keep the stuff around up to 2 kilohertz. So what this means in particular here is that our delta F, which is F2 minus F1, is 500 hertz. And we're also going to have pass band ripple of 0.01, so 10 to the minus 2, and stop band ripple 0.01, so again 10 to the minus 2 here. So for this particular filter, which has got quite a high sampling rate here, passband and stop band are a long way down from 96 kilohertz. And you can see already here that the ratio between FS and delta F is quite large. So this is going to lead a relatively large number of taps. Let's have a look at the order for this one. N is 2/3 log to the base 10 of 1 over 10 times delta 1, which is 10 to the minus 2, times delta 2, which is another 10 to the minus 2, times Fs over delta F. Now Fs is 96 kilohertz, divided by delta F, which is 500 kilohertz. So we can cancel out a bit of those 500s into 96, go 192. This in the bottom is all 10 to the minus 3 in there. So actually that's 2/3 log to the base 10 of 10 to the 3 times 192, which is 2/3 times 3 times 192. That cancels, so that's 384 taps. That's a big filter. But actually, that's sort of typical for what you might want to build an FIR filter for. They can get that long. Now let's suppose we were going to use this filter for decimation. We want to use this for decimation of 96 kilohertz down to 6 kilohertz. That's decimation by 16 times. So that means we want to go through a decimation filter Here's our low-pass filter. Decimate by 16, and here we've got 96 kilohertz, all the way down to 6 kilohertz. So we compute the filter at what sample rate? What's the sample rate that we're going to run this filter for in this decimation process? Anyone remember from last week? We've got a low-pass filter here running at 96 kilohertz. We then downsample by 16 to 6 kilohertz. What's the effective sample rate that we need to run the filter for? 6 kilohertz, yeah. We always run the filter by joining these together. We don't need to run it at 96 kilohertz because we're throwing away all but 1 out of 16 of the samples, which means that we work out our filter to never calculate those values in the first place. So we only run the filter effectively at the 6 kilohertz. So we compute the filter at n times fs out, which is, in our case, 384 times 6 kilohertz, 6 times 10 to the 3. So that's about 2.3 times 10 to the 6 multiplies per second. So that's the computation cost for this filter. This is how much it's going to cost you to downsample from 96 kilohertz to 6 kilohertz in one go. And the filter that we chose down filters from 2 and cuts off by 2.5 kilohertz. So it's cut off by the time we get to our 3 kilohertz Nyquist limit. So this is a sensible filter to use for this decimation process. So now we can see this is an example of what we might want to do, but we might be able to do this decimation downsampling process in more than one step. So suppose instead of doing just the one step here, let's look at a multi-stage version. So the multi-stage version, decimation by 16 is decimation by 8 times 2. So what we could do is replace this decimation by 16, instead of having a low-pass filter followed by decimation by 16, we're going to replace that by a low-pass filter 1, followed by decimation by 8, and then a low-pass filter 2, followed by a decimation by the final 2. So here, the sample rates that we've got in this one are 96 kilohertz here and 6 kilohertz here. For this one, we've got 96 kilohertz coming in. In the middle, we've decimated by 8, so we've got 12 kilohertz, and then at the final output, we've got our 6 kilohertz. Now let's have a look at the filters that we need to design for each of these two stages. And actually what I'm going to do is I'm going to start from this far end. Start with stage 2. So this is, call this one stage 1. And this one, stage 2. So let's start with stage 2. Because actually what we're going to see is once we know what stage 2 does, we can design stage 1 to prepare us for what we're going to do in stage 2. So I know it's looking a little bit backwards, but it's like project planning. You start from where you need to deliver. Yes?
This, the single stage one you did.
Yes.
What's the decimation amount, just arbitrary?
So in the single stage 1 that we did here, the decimation amount was, we chose this decimation to be 16 times decimation here. What we probably should have done is to choose the decimation first and then choose a filter to fit that decimation. So this is just an example. We're using 16 times decimation as an example. So if we wanted to decimate by 16, here we're deciding to split it into a decimation by 8 followed by a decimation by 2. It depends really what you want to do your decimation by. If you want to decimate something by 12, you could split it into decimation by 4 followed by decimation by 3. But we'll see that in this particular example, we'll end up with the whole system being more efficient than it would have been, as in lower computational cost, than doing it in one go. But let's look first at the stages that we're going to go through in terms of what decimations that we want to make. So for this one, let's just pick out the decimation process. So we've got 12 kilohertz coming in, we've got a low pass filter 2, and out from here is we've got a decimation by 2 with 6 kilohertz coming out. So in this particular case, let's have a look at our the bandwidth of what we're doing. So here's our 0, here's our F. We've got 12 kilohertz as our bandwidth. We'll assume that this is our Nyquist 6 kilohertz limit, and so somewhere we're assuming that we're given a signal that is within the Nyquist limit. So we're going to assume that our 12 kilohertz is actually well behaved up to that point. But what we want to get to before we decimate it, the filter that we're going to need, this is our signal, the filter that we're going to need, we need that to cut off before 3 kilohertz. So here's our 0, 3 kilohertz, 6 kilohertz, 9 kilohertz, 12. We need to make sure that we've got a filter that cuts off by 3 kilohertz as part of our decimation process. And actually, because of what we had specified before, we're going to want that filter to cut off by 2.5 kilohertz, and that the F1 edge to be 2 kilohertz. And so this is our transition band here. Delta F is our 500 hertz. So that's our transition band for that filter. So this matches the filter that we wanted for the far end. We've also got up here, 2.5 kilohertz is down here, so up here, this point is 9.5 kilohertz. Up here with 9 kilohertz at the top of the filter there. So what we can see here is that the filter that we're going to design will chop out everything between 2.5 and 9.5 kilohertz. So anything in that range, we're going to remove with our low-pass filter. So this, yes, sorry, my mistake. Should be 10 kilohertz there, yes. Quite right, thank you. Now, this filter, although it's got the same delta F at 500 hertz, the sampling rate is only 12 kilohertz instead of 96 kilohertz. So from the formula that we had on the previous slide, let's just pop the formula back up at the bottom here, you can see this ratio is better. The sampling rate is lower, so therefore the filter size for this one is going to be easier. We'll do the calculation in a moment, but this is just looking forward a little bit to say, okay, this is going to be a simpler filter to construct. But now let's look at stage 2. Well, sorry, we did stage 2. Let's have a look at stage 1. So now we need a low-pass filter here and a decimation by 8 block here. We've got 96 kilohertz coming in. We've got 12 kilohertz going out. So in total, this is our, let's put a bit of a gap there because we've got 96 kilohertz here as our sampling rate. We've got 48 kilohertz is our Nyquist, and we've got 12 down here, and our 6 kilohertz here. Now, if we zoom out this bit, let's zoom out this to this range. .12, 0 at the bottom, 6 kilohertz. This is 3 kilohertz here. We wanted to keep everything up to 2 kilohertz. But if we look at what's going to happen to it at the next stage, everything between 2.5 kilohertz and 9.5 kilohertz is going to be removed at the next stage. So that means we don't have to have a really sharp cutoff filter here. Instead, as long as we're by 9.5 kilohertz, as long as we've cut off by there, that's the thing that we're going to keep with the next stage of the filter. So actually everything in this range from 2.5 to 9.5, this is a don't care region for this filter. We can do anything we like with the filter across this range, and we don't mind because it's actually going to be filtered out after that. So actually what we do, and because that ramp is going to take us off there, we're allowed to have our transition band all the way from 2 kilohertz up to 9.5 kilohertz. So this is now our delta F is 9.5 kilohertz minus 2 kilohertz, which is 7.5 kilohertz. This is our transition band. So now we've got an FS which is 96 kilohertz, but a delta F which is 7.5 kilohertz. So we can see that now, instead of the transition band, which was 500 hertz in our original one, we've now got a much wider transition band, and that's going to make it much easier to design this filter. So we've now got a decimation process with 2 filters, but each filter is much easier to design than the single filter that we originally had. So let's pull all of these together into one process. So we're now going to have 2 successive filters. Now, one of the issues here is that the pass band is applied twice. So the ripple doubles. So if we have some filter F1 and a filter F2, the total ripple, if we look at 1 minus delta 1, being 1 minus delta 1, let's call that 1, 1 minus delta 1, 1, 1 minus delta 1, 2, where this is from stage 1 and this is from stage 2, it's actually equal to 1 minus delta 1, 1 minus delta 1, 2 plus delta 1, 1, delta 1, 2, and this is small. So that's approximately 1 minus delta 1, 1 plus delta 1, 2. So the ripples sort of add up. So typically, we use delta 1, 1 equals delta 1, 2 equals delta 1 over 2. In other words, we divide the ripple by 2 if we've got 2 stages when we use that. So that's something that we have to do. Just that makes our filter slightly more expensive because we've reduced the ripple. So let's bring this all together. E.g., if delta 1 was equal to 0.01, then delta 1, 1 equals delta 1, 2 equals 0.01 over 2, which is 0.005. So bringing it to calculate the full cost of both stages, cost of stage 1, N1 is 2/3 log to the base 10, 1 over 10 times 10 to the minus 2 over 2, that's our split delta 1, times 10 to the minus 2, that's our delta 2, times the sampling rate that we had, which was 96 kilohertz, divided by, this time, 7.5 kilohertz, which was our longer transition band that we had. If we calculate that out, that's about 28.1, so we use N equals 29. This is much smaller filter than the 380 something that we had first time round, and it's all really down to the much longer transition band that we've got. So that means now the cost for operating is the sample rate, and if we look at our stage 1, we're running at the lower of the sampling rate, which is 12 kilohertz. So the cost for operating the filter is the lower sample rate, which is 12 kilohertz, 12,000 times N1, which is 12,000 times 29, which is 348 times 10 to the 3, multiplies per second. Now let's look at the cost of stage 2. For this one, N2 is 2/3 log to the base 10 of 1 over 10 times our delta 1, 2, which is 10 to the minus 2 over 2 times 10 to the minus 2, times, this time, the sampling rate, 12 kilohertz, divided by the transition bandwidth, which is our 500 hertz. That's about 52.8. So we'll use N equals 53 for that one. And for this one, the cost of operating is, this time it's the lower sampling rate, which is 6 kilohertz times N2, which is 6,000 times 53, which is 318 times 10 to the 3, multiplies per second. So the total cost is 318 plus 348 times 10 to the 3, which is about 666 times 10 to the 3. Multiplies per second, which is much less than our 2.3 times 10 to the 6. Multiplies per second for single stage. So we can see here that we've saved pretty much a factor of 4 by being able to use this two-stage version. So this is occasionally useful, that it says rather than trying to do everything all in one go, let's simplify the process over 2 stages. And the key thing in why this works is, for one thing, the second stage operates at the lower sampling rate, but really it's this important fact that for the first stage there's a huge don't care region, because we're going to filter that out once we get to the second stage. And so that means that our transition band can be much wider. That's really why this works. Okay, so that's the multi-stage, multi-rate part. It's just showing that if you want to do this process, it's very much worth looking at multiple sections for this. There's some practice at this in the tutorial. It's not always guaranteed that this will work. You might think, oh, maybe we can split it into 3 stages. 4 times 2 times 2, that may actually end up being more expensive because you're just paying more to do that. Doesn't necessarily mean splitting it down as much as possible is going to be the best way of doing it. So you may have to just experiment with things to find out which works and which doesn't work. Also notice for this one that when we were doing this process, we downsampled by 8 followed by 2. You could downsample by 2 followed by 8. That might not give you such a good advantage of this. So if you want to try this at home, you can try out some different values to find out how this works. Okay, so at that point, what I'm going to go on to now is the module evaluation questionnaire for a bit. This I want to allow 10 minutes for, and therefore I will start the next lecture late enough so that we can have 10 minutes to go through this. And we'll start again with the next lecture at 5 past on the clock. But I don't need to record this bit, so I'll just turn this off of the recording for now. So if you're watching by Panopto, you don't have to hear the module evaluation questionnaire happening.